Welcome to the video tutorial on relationships. We've already looked at correlation as a descriptive statistic, and we want to take this a little bit farther, but first we're just going to review it real quick. Remember, we talked about R being the correlation coefficient. We have that R is between -1 and 1. If R is near 1, then the relationship is linear and it's strong. Okay, and this is the absolute value. So if it's near -1, it'll be strong. If it's near +1, it'll be strong. If it's near 0, then the linear relationship is weak. Probably not much really going on there. If R is greater than 0, then there's a positive linear relationship. If R is less than 0, then there's a negative linear relationship. Here's some examples. Here R is equal to 0, and it's really hard to see any sort of pattern in this data in terms of a relationship between X here and Y. Now, here we can see R is equal to 0.5, and if I look, I can see the corners are empty over here, and I can sort of see that there's maybe some clustering in the middle, that it's coming together, but it's a weak relationship, and it's positive because these corners are empty. Here is a moderate negative relationship, and here you can see these corners are empty. And you can see that more and more of a pattern is showing up in this picture. Here's a strong positive relationship. You can see the corners are really empty. Most of the data is clustered up. And it looks like in a linear fashion, you can really start seeing the linear here. And here's a very strong negative relationship. You can see R is equal to -0.99. And you can see here that it's close to a line. That's what we mean by a linear relationship. The word linear, the first 4 letters are line. Okay, so this is what we've been looking at. So, key here is it's linear, but it really doesn't tell us how X and Y are related. It just says, hey, look, they seem to be related, but it doesn't tell us something that's really usable. And also doesn't tell us, what if we want to know the effect of X on Y? And that's what we're going to be after. So correlation is useful, but only tells part of the story. Okay, we can use a modeling approach to discover the effect of X on Y. And when I say modeling, this is our first look at actually using what I would consider a model in the traditional sense of having a mathematical model. So, regression analysis is what we're going to be talking about, uses a linear model, and notice the line is in linear, to express the relationship between X and Y in a mathematical form. And here's an equation of a line. Y equals beta 0 plus beta 1 x. This is a simple line. You might have seen it as mx plus b in high school, but we're going to go with this convention because later we're going to have other variables that we might put in here, and mx plus b just doesn't work well in that format. Okay, so here beta 0 is the y-intercept. It is the mean of y when x equals 0. And here beta 1 is the slope. And you can go, well, I don't remember any of this from high school, and why do I need to know this? Well, it turns out that this is really useful because the slope is the change in y for a 1-unit change in x. It's telling me how y changes when I change x, which is an effect, right? Beta 1 tells us the effect of changing the value of x has on the value of y. So I can see how x changes, any changes in x influences the value of y. Okay, so from a statistical perspective, we've got to talk about it from data, right? There it's theoretical, but we're going to see observations. We're going to have a bivariate random variable, x sub I, y sub I. And what we're going to do is we're going to say x sub I and y sub I are related through this linear relationship. Here, this epsilon I on the end is the error between the point xi and yi. This is the point, and the line that we're going to fit to it. Okay, so we're going to be fitting a line to it, and we'll assume that epsilon I follows a normal distribution with mean 0 and variance sigma squared. And we're not going to really focus on that right now because that just gets in the way of what we're trying to understand here. So what does this mean? So, for example, here's some data. It goes around from -2 up to looks like 6.5 or so. On the x-axis and on the y-axis, it looks like it goes maybe from 3 to 9. But you can see that there is some sort of relationship here. If I looked at this, I would definitely see some sort of relationship, and it does look like it's a line, or could be approximated by a line. I fit a line to it. So here I've fit a line to this, and this would be a regression line, and this epsilon I is how much I missed. Notice that all the points don't stack up on that line. The line is a model for the relationship. It doesn't mean that is the relationship. It's a model for the relationship. And not all of the points stack up on that line. It looks like there's only one point that looks like it's even on the line. This one looks close, and then there's this one, but the rest of them don't hit the line at all. So this is what we're talking about with errors. And if I can highlight all of the errors here, because this is what we have by our epsilon I, and our goal here is to minimize the total errors made. So we're going to add these up. We're going to total them. We're going to sum them up, and we want to minimize that in some sense. Okay, we're going to minimize it in what's called the least squares sense, and this is called a least squares line. You might have heard people talk about I use least squares regression. Well, that's essentially what least squares regression does, is it minimizes the distance of the point to the line. Okay, that's all it does. And the errors are the distance of the point to the line, and that's all epsilon means. All right, so how do I use this? Well, I have here my data and my line, and if I move x along this direction by 1 unit, if I go from 1 to 2, y looks like the line goes up by 0.57. Okay, so it's telling me what the effect is. So if we increase x by 1 unit, we would expect a 0.57 unit increase in y. So it's telling us what x does to y and by how much. That's the key. But it's not the whole story yet. We're going to work our way through it. But here's why we're trying to use a line, because we can actually try to quantify these things like what is the effect? All right, so we can actually write this equation down. So here I've written down the equation of this line through this data, and that allows me to actually interpret things. So this is when I talked about a mathematical model. It's a formula that tells me when I plug in x, I can get a y, and there's a little hat on here, which means it's the estimate of what y would be, because notice that the line here, not every point falls on that line. So it's a mathematical model for the mean of y for a given x. And you could use this roughly for a prediction, but it's only going to give you a point estimate, and that's what we're going to talk about, is how to do inference on these without going crazy. And so we need to talk about a few other items before we can actually go and try to employ this in SPSS, but we do have here the framework for fitting a line to some data.